Hello, differential equation students. Let's take a look at the section 1.2. This is about initial value problems. So this is about initial value problems. So to do that, let's take a step back and try to understand a few things about the solutions, and then we will move along. Excuse me. So we have a differential equation, very nice differential equation, which is y prime is equal to y. Now, we can verify, I'll let you do that. You can verify that this is a solution. So it's very simple, by the way. If you take a look at, the y prime, it's a nice function. So this is called, by the way, more precisely, we can say this is explicit solution, right? Explicit solution, because in the previous section we talked about the implicit solution. In general, for the rest of the semester, for the rest of the videos, whenever we talk about the solution, we allow that solution to be an implicit solution. It does not have to be a function. But in general, some books, some literature define solutions as explicit solution. For our purposes, for the rest of the semester, whenever we say a solution, we allow implicit solutions. So here's a solution. Here's a function, which is y is equal to e to the x. So if you take a look at the right-hand side, that's a function, by the way. That's also a differentiable function. So it satisfies both the properties. If you take a look at the right-hand side, which is y prime, if I find the derivative of the e to the x, which is e to the x itself, and which is equal to the original function, which is the left-hand side. I'm sorry, which is the right-hand side. Right. All right. So here's I started with the left hand side. I ended up with the right hand side in here. And so therefore, this is a solution. The question is, would this be a solution? I'm multiplying a number 2 here. I'm multiplying a number 2 here. Would this be a solution? Let's quickly take a look. So again, this is a nice function. It's a differentiable function. No problem there. If you take a look at the left-hand side, the left-hand side is the y prime. The derivative of the 2e to the x, the derivative of that would be 2e to the x again, which is same as the y. And so therefore, this is also a solution. What about this? By the same token, you can verify that this is also a solution. So as a matter of fact, this number does not matter. This number does not matter. You can choose any constants, even including 0, because 0 is also a solution, because the derivative of 0 is 0 itself. So that is also a solution. So in general, we can say that function y of x equals a constant times e to the x is a solution for any arbitrary constant, for any real number, c. And since I can change the c, and I can't change e to the x, right? The e to the x remains e to the x, but I can change the c. So I have a wide variety of the c that I can choose. So I have a whole parameters that I can choose. So we call this as one parameter family of solutions. So we have infinitely many solutions now. So for this particular differential equation, right? For this particular differential equation, you have infinitely many solutions. And although it's infinitely many solutions, it's not like any functions can be a solution. Any function which is of the form a constant times e to the x would be a solution. As a matter of fact, if I have this function, y is equal to e to the 2x, that would not be a solution, right? Y is equal to 2e to the x would be a solution, right? But y is equal to e to the 2x would not be a solution. So we have infinitely many solutions. We have family of solutions, and that family is e to the x family. Any constant multiple of e to the x would be a solution. So we call that as a one parameter family of solutions, and that parameter here is the c, and we say this is an arbitrary constant, right? For any arbitrary constant c. Let's take a look at this one, the second order differential equation, which is y double prime plus y prime. Y double prime plus y prime is equal to 0. Now the question is y of x equals sine x a solution? Let's quickly take a look. So let me take a look at the left-hand side, which is y double prime plus y, and my y is equal to sine x. So therefore, let's see what happens to the first derivative. You're all experts in the derivative. So the y prime of x is equal to cosine x. And the y double prime of x of the same function is going to be negative sine x. So if I plug this information, back in here, you would agree with me that I would have Let me change the color so you can see it better. So I'm going to keep this as in blue. I'll change this to, let's just say, purple. I'll keep the other one in blue. I'll keep this one in green. So now this is the purple, and this is the green. And so if I plug it in, ladies and gentlemen, you would agree with me that this y double prime is cosine x, right? And y double prime is sine x. What am I thinking? I think I messed it up in here. Let me rewrite it. Y double prime is green plus y, which is a black. If I simplify that, the y double prime is negative sine x, and the y is the positive sine x, right? Y is the positive sine x. When I add these two together, you agree that I'm going to have a 0. That is my right-hand side. So therefore, that's a solution. Again, you can verify that cosine x is also a solution. Since y is equal to sine x is a solution, in this case, a constant multiple, right? Any constant multiple of sine x would also be a solution. You can verify that, right? If you can verify that. And so now we have one parameter family of solutions. Since cosine x is a solution, another constant, it does not have to be the same constant. This could be 2 and this could be 3. This could be 3, this could be 4, this could be 5, this could be 2020, this could be negative 2020, this could be positive, million, right? So it could be anything, right? The C and D does not have to be exactly one the same. So now I have another function with another parametric family, right? Another parametric family. So we have, as a matter of fact, two families of functions. One is a sine x family, the other one is a cosine x family. If you replace the C by C1 and D by C2, right? Now this together, I know you go ahead and verify on your own whenever you're free, right? This together would be a solution to this particular differential equations. And now how many parameters do I have? I have two parameters. I have a C1 and I have a C2. Both are arbitrary constants. It could be any real number. And now that is a solution. So we call this a two-parameter family of solutions. So for example, in general, by the way, when you have nth order linear differential equations, right? So when you have nth order linear differential equations, you will have n parameter family of solutions. So for example, I'll give you one more. If you have this differential equation, which is y triple prime minus 3y double prime plus 2y prime is equal to 0. That's a third order linear differential equations. This has three parameter family of solutions, and that would be y is equal to some constant plus another constant times e to the x plus another constant times e to the 3x, right? For some of you, it might look like I'm pulling a rabbit out of the hat, looks like a magic. This is not mathemagic. This is mathematics. You will see how to get these solutions in the later sections, but right now you can verify, right? You can verify, see if this is a solution or not, right? By finding the first derivative and plugging it in here, and finding the second derivative and plugging it in here, finding the third derivative and plugging it in here, see if this is a solution or not, right? We'll verify that when you have some free time. All right, now let's take a look at the initial value problem. So we talked about, family of parameter family of solutions, right? One parameter, two parameter, and so on. Now let's take a look at the initial value problems. Initial value problems are very nice problems. So it's basically, the initial value problems have two components. The component number one is your differential equation, the DE, and then you're going to have an initial condition. I'm going to call IC, right? We're going to have an initial conditions. It could be, y of 0 is equal to 1, y of 0 is equal to 2, anything. It could be anything. And these two together constitutes an initial value problem, which we call IVP, right? So a differential equation. So in general, if I say y prime is equal to y and y of 0 is equal to 1 is a initial value problem. Now, these initial value problems are not going to have parameter family of solutions. As a matter of fact, we can exactly figure out what those parameters are. So we just learned this from the previous, a couple of minutes ago, that y prime of y, the solution to the differential equation, not the initial value problem, just the differential equation part, right? Is we know that it is y of x is a one parameter family of solution, which is c e to the x. Now, this condition right here, that initial condition that y of 0 is equal to 1 is going to help us to figure out this particular c. Let me show you how do I do that. So now what I'm going to plug in x equal to 0. When I plug in x equal to 0, ladies and gentlemen, into this equation, you're going to agree with me, I'm going to have c e to the 0, which is equal to c times 1. And y of 0 is given to me here as is equal to 1. So now I have an equation for c, and that is 1 is equal to c times 1. So therefore, c is equal to 1. And so therefore, although this differential equation in and of itself has a solution, one parametric family of solution c e to the x, combined together with an initial condition, the solution for this problem is y of x, not for the differential equation, but for the initial value problem is y of x is equal to 1 times e to the x. So therefore, we can say e to the x. And that's it. We have only one solution for that. We don't have any other solution for this one. Let's take a look at another initial value problem. Suppose if I have a similar one, just say I have this initial value problem, which is y prime is equal to y and y of 0 is equal to, let's just say 3. What would be the solution to this? Again, y prime is equal to y is going to give you the one parameter family of solution, which is y of x is equal to c e to the x, right? And y of 0 is equal to 3. When I plug it in, y x is equal to 0, that's going to be y of 0, and that is equal to 3 from here. And now if I plug in 0 here, right? Now if I plug in 0 here, and that is going to tell me this is c times e to the 0, which is equal to c times 1, which is c, right? Now, so this tells me, these two together, right? These tells me that c is equal to 3, and therefore the solution to the IVP, which is y prime is equal to y and y of 0 is equal to 3, right? This IVP is y of x equals 3 e to the x. So that's how we can find these constants. And we talked about these, this particular problem, right? Another differential equation. So I'm going to give you a u-try problem here. So consider this particular problem. That is initial value problem, y double prime plus y is equal to 0. And I'm going to give you initial conditions. In this case, it's going to be more than one, because we're going to have more than one parameter, because this one has two parameter family of solutions. So I need two conditions, right? So the first condition is I'm going to say y of 0 is equal to 1 and y prime, the derivative of 0, is equal to, let's just say 0. Now using these conditions, right? Let's take a look at this initial value problem. Anyway, I'll give you this, right? But you have to try this. We know that the parametric family for this one, the parametric family of solution is the two parameter family of solution is y of x equals c1 times sine x plus c2 times cosine x, right? Now plug this information, right? Find the second derivative, right? Plug this information that y of 0 is equal to 1 in this, and find the derivative, and plug in y prime of 0 equal to 0, figure out the c1 and c2, and that's your exercise for you. And that's pretty much is the basic initial value problems right there. Let me give you one other problem. Let me give you one other problem right here, which is this. Suppose if you have a differential equation which is something like this, right? Y prime is equal to y prime plus 2xy squared equal to 0. Go verify this as a differential equation, not an initial value problem, differential equation, right? This one has a one parameter family of solution, and that one parameter family of solution is y is equal to 1 over x squared plus c. 1 over x squared plus c. That's your one parameter family of solutions. Now I want you to figure out the solution to this initial value problem, which is y prime plus 2xy squared equal to 0. Then I'm going to give you an initial condition. That initial condition is y of 0, right? Y of 0 is equal to 1. Y of 0 is equal to 1. Now, let's take a look at this initial value problem. This is an initial value problem, ladies and gentlemen. The reason because this is a differential equation, but it's not by itself. It is accompanied by an initial condition. For that reason, this is an initial value problem. This initial value problem can have only one solution. And then now you figure out the C value and tell me what would that be, right? And so that's pretty much just some basic things with the initial value problem. Initial value problems are easier to solve. There's something called the boundary value problems. We'll talk about it later, but they are relatively harder to solve. But initial value problems are relatively much easier to solve. And in terms of solving the initial value problem, we have a wonderful mathematician, our great mathematical grandfather Pickett's. He came up with a wonderful theorem. So he guarantees existence of a solution and uniqueness of a solution. So he guarantees if you have an initial value problem that satisfies certain condition, he guarantees that you're going to have a solution to that one. Not only a solution, you're going to have only one solution, not more than one solution. So let's take a look at what is the theorem and how do we use the theorem for our practical purposes. All right. Now let's take a look at the initial value problem. Very generalistic initial value problem is this one, right? That y prime is equal to f of x comma y, and y of x naught is equal to y naught, right? Y of x naught is equal to y naught is the initial value problem, because you have a differential equation and you also have initial conditions, and this is a more generalized, an initial value problem, just like we looked at it before, right? This is a special case. It's a special problem. Here's the general case of an initial value problem. So the Pickett says the following: if the function, this function right here, this f of x comma y, that when you write the differential equation in the normal form, this f of x comma y has the following properties. Number one, the function is continuous. Number two, the partial derivative of f with respect to y, not with respect to x, the partial derivative of f with respect to y, if that is also continuous. So if this f by itself is a continuous function, I'm going to say CTS, I mean by continuous, and the partial derivative of f with respect to, not with respect to y, not with respect to x, with respect to y, if this is also continuous on any region, on any interval, right? It may not be on the entire real line. It might be partially on the real line. That's okay. If it's even partially, it's okay. Then he says, this initial value problem will have a unique solution in the neighborhood of these initial values. What do you mean by initial values? This is x naught and y naught, right? This is x naught and y naught. So here's my x naught value, and here's my y naught value. So here's my initial condition right there. Right? Here's my initial condition right there. So he says in the neighborhood, as long as this function is continuous, the partial derivative is continuous, in this neighborhood, a smaller neighborhood in a rectangle, this function will have unique solutions. What does that mean? I will not have another solution for the same initial value problem, something like this, although it's passing through this one. but I will not have, excuse me, I will not have a solution that passes through this particular same initial point, initial value. So he guarantees that. So let me give you an example. So let me take a look at this, a nice differential equation, which is y prime is equal to y. As simple as that, right? And let's just say y of 0 is equal to 0. So geometrically speaking, x naught is 0, y naught is 0. So therefore, our initial condition is this value right here, because x is 0 and y is 0, right? Now, what is my f of x comma y? Here is my f of x comma y. As a matter of fact, there is no explicit x in there. It's just a function of y. We know that the function, this f of x comma y, which is y, is a continuous function. No problem there. That's a continuous function. And if I find the partial of f with respect to y, again, if you don't know partial derivatives, there are plenty of YouTube videos. Take a look at them. I'm sure you would know them from your calculus too. If you don't know, there are a lot of videos. You can do that. Otherwise, come and talk to me. I'll be happy to help you. So if you take a look at the partial derivative of f with respect to y, that's 1. That means basically we're going to treat x as a, to give you in simple terms, we're going to treat x as if it's a constant. We're going to treat y only it's a variable. So here it's, I'm going to treat y as a variable. If I find the derivative of y with respect to y, which is 1, and that is also a nice continuous function. So it satisfies Pickett's theorem. It satisfies the Pickett's theorem. So we can guarantee the solution to this initial value problem in this any in the neighborhood is going to be unique. You will first of all you will have a solution. He guarantees the existence, and second, he says there's only one solution. You will not have more than one solution. So that's what Pickett guarantees on this particular one. There are some wonderful implications of this, and we will talk about those wonderful implications in the next video.